Good morning. We continue our lecture on crystal defects in metals, and here basically we have considered that concept of crystal defect was introduced, and what was mentioned last class is that although that initially that concept of dislocation was necessary primarily to explain why real crystals have low strength, real crystals have low strength, and also we have seen that too for homogeneous nucleation of dislocation, either homogeneous nucleation of dislocation in a crystal or to move or to plastically deform an ideal crystal, you need a very high order of strength. And Taylor introduced this concept the way back in 1930s. 1930s, I think this concept of dislocation was introduced by Taylor, but it was not until subsequently later, when there was a direct evidence of presence of crystal defects like dislocation. Now, one of the simplest way of looking at dislocation is a chemical that H-pit technique. So, if you polish a metal and electropolish, and there are special etching techniques, and dislocations we know that they cannot either they will be endless, or if they have to end, they will end on a free surface. So, which is shown over here. So, suppose there is a dislocation in a solid, it cannot end, it can be a endless loop within, but if it intersect, but it can intersect a surface. This is the end point of a dislocation. Now, depending on the nature of this dislocation, so there will be lattice disturbances here. So, there will be one kind of lattice disturbance in case of an edge dislocation, another kind in case of a screw dislocation. And when you a polished surface, when it is chemically etched, this is where the atoms are in excited state. You can see the higher energy state. So, here the dissolution rate will be more. So, it is possible to this portion will be attacked more than the rest, and this develops a pit, and pit has a certain geometry, and depending on and similarly this pit along a screw dislocation will have another geometry, and in fact when you look at that microstructure, look under under a microscope, you may see that these are the grains, and within the grains this type of pits have developed, and they can have different shapes depending on what is this plane, what is the crystallographic orientation of the plane, and how is the dislocation oriented with respect to this plane. Now, rate of dissolution is actually a function of local strain field, local solute concentration, and plane geometry. So, this has been one of the earliest proof, but still it was not a very direct evidence. And later on, when electron transmission electron microscopy techniques were perfected and developed, and sometime in 50s and early 60s, there have been lot of work has been done, which showed conclusively direct evidence of presence of crystal defects like dislocations in crystals. And seen in transmission electron microscope, you examine a thin foil. Suppose this is a thin foil, and here I am visualizing, let us visualize, these are the regular these atom planes which are arranged, and this is an edge dislocation. This simulates a pictorial representation of an edge dislocation. Now, when this beam passes through the region which does not contain the dislocation, it will pass through and through, and when it strikes that image plane, it is focused on that image plane, it will appear, this area will have a bright contrast. Whereas, look at what happens when this beam passes through the region where there is local lattice disturbance, something like this. It falls on this plane and it gets diffracted. So, it does not strike the image plane. So, therefore, here locally there will be the intensity, there will be an intensity contrast, there will be a diffraction contrast, and this line will appear dark. And here also there is no defect. So, it just passes through, it is not getting reflected or diffracted. So, basically from region containing the defect. So, what you will find that dislocation will appear like a line. And transmission electron microscope has several other advantage also. This electron beam, it has a wave character. So, you can also record diffraction pattern. So, in that case, see what is done here, if you block this transmitted beam and you can remove that projection lens, then on the image plane these diffracted beams will fall, and these diffraction beams will give a pictorial description of the orientation of the foil plane. Now, and here also when you are looking at this microstructure, there is a provision to tilt the sample, and if you tilt the sample here, you can also get an orientation where this line will disappear. That means, this line beam will pass through and through. By this technique, these two techniques, that means local, that selected area diffraction to find out orientation of the foil plane, and by rotating the crystal and finding out when this dislocation disappears, it is not only possible to see the crystal defect, but also to find out Berger vector of the dislocations. And this, I do not think that we can cover this is in further details, I think, which is not in within the scope of this particular course, but you can refer to any standard text on transmission electron microscopy and electron diffraction, which will give you methods of observing direct observation of dislocations in crystalline solids and determination of the orientation of the foil plane and the dislocation direction in which the dislocation is lying and its Berger vector. So, you can clearly establish whether you see a dislocation, whether it is an edge dislocation, screw dislocations, or a mixed dislocation. There have been many other methods which gives indirect evidence of defects in materials. One of the simplest thing is to measure certain physical properties. Say, like one of the physical property is that you can measure resistivity. Now, resistivity, we know that if you increase the vacancy concentration, you can visualize it like this. If you increase the vacancy concentration, in a way you can say that effective area decreases. So, therefore, if you increase vacancy concentration, this actually that basically this will, that electron movement, I mean electron which is the carrier of electricity, it will encounter some additional resistance, and this change in resistivity of a material will be directly proportional to the concentration of the vacancy. So, NV is the number of vacancy and rho V is the change in, this represents the change in resistivity when you introduce one vacancy in the lattice. So, therefore, if you have NV number of vacancy in the lattice, this will be the change in resistivity, and we have found out an expression for number of vacancies that can exist in a material at a particular temperature, and this is given as N is the total number of lattice sites, N exponential minus Q V over kT, where K is the Boltzmann constant and Q is the energy which is required to create a vacancy in the lattice. So, this is a very simple expression and you can find out resistivity easily of a material. And in fact, one of the earliest work that was done, if you take a sample, say a small piece of say sample. So, earliest work was done on gold. It was heated to a high temperature. When you heat it to high temperature, a lot of vacancies, that concentration of vacancy will be much higher than that you get at room temperature. Now, if you cool it very fast, in that case what you are doing? You are retaining excess vacancy at room temperature, or you can quench also sub-zero temperature to ensure that vacancy does not diffuse out. You can quench it in a low temperature bath, and then what you do? You measure the vacancy or measure the resistivity of the material at 0 degree centigrade. So, you can now have a set of data by heating gold to different temperature, quenching to a sub-zero temperature and measuring the resistivity at a constant temperature, say 0 degree centigrade. Now, you have a set of resistivity data as a function of the temperature at to which the sample was heated, and we can make, if you assume that since we are quenching it very fast and this temperature is very low, the these defects cannot diffuse out and they are held within the crystal. And what you find, actually the resistivity increases with as you increase the temperature. And if you make a plot, if you look at this, if you plot log of change in resistance against 1 over T, you will get a linear plot something like this, and the slope of the plot can give you an estimate of the energy that you need to create a vacancy. And indeed, with the availability of TEM, such samples were then looked or examined under electron microscope, and when you look at electron microscope, what you see as actually something like this. There are rings here which are actually really stacking fault, and we may recall that this is the type of dislocation that you get here within the plane. Say we know that the layers in face centered cubic crystals, this 1 1 1 plane, they are arranged in this sequence A, B, C, A, B, C. Now, what is happening here? These vacancies, they are concentrating over here. So, this area, this vacancies have come here and this goes out. So, what you have here, a sequence within this, you have a sequence A, B, then you have C, and here the lattice, this plane will get slightly distorted, this plane will get slightly distorted, and there is a stacking fault in this stacking, and this fault we have been told, you have been told that this type of fault is known as Frank, formed due to formation of Frank partial dislocation. And this dislocation, here is the extra plane of atom, this is the slip plane, and this is the Berger vector of this, and this Berger vector will be A by 3 1 1 1 type. And here when you are passing this TEM, that electron beam, so from here and here you can see there will be the thickness, say that means out of few layers, because when you see the foil, these foils are extremely thin, they contain only very few, they may be of the order of maybe around say 100 to 1000 angstrom, that kind of thickness, these foils will be very thin. And here you can clearly see that when this passes through this line here, so these planes are distorted like this gets diffracted out, So, the beam which will pass through this region, you will find that it will be a diffraction contrast and a ring like this, and by measuring the dimension of the ring, people have calculated the stacking fault energy also can be calculated. Now, we are talking about surface defects, and the first surface defect in terms of the dislocation concept that was introduced was the stacking fault, and stacking faults also can be seen easily under the microscope, and one example has just been cited. Now, but one of the simplest surface defect that we know of, and you can see these defects under optical microscope, these are grain boundary. We know that metals are made up of, when you look at the microstructure of a metal, actually what you see is several grains, they are oriented randomly, say something like this, you see these grains, another grain, this is how the microstructure may look like. So, these grains each may have different orientation, this will be the appearance of that microstructure. Now, point is, this is the boundary. Now, this boundary, two things, this boundary, it is on the microscope, and the microscope what we see is a line, but in reality it is a surface. Now, this surface may be bent like this or be bent like this, and that will depend on the shape of these grains. It will depend on the shape of the neighboring grain. It will also depend on the orientation of the grain, shape and orientation of the grain. And we can easily visualize if these crystals are randomly oriented, this atomic structure, the way the atoms are arranged on this grain boundary, this will be very difficult to visualize. Of course, so in a way what we can say that this boundary, although we see this easily, but its structure is extremely difficult to visualize, what will be the nature. Now, let us take up a case, this is pictorially what I am representing. So, this is one grain, this is the another grain, and we very often will find that these grains, these atoms, there may not be any match, they will be randomly oriented, like here there is an atom here, there is an atom here. So, there is no no exact that crystallographic match over here, and in this case what happens, you can see this boundary easily, because along the boundary there is some amount of disorder, within the grain there is some crystalline order is there, atoms are arranged in a periodic fashion, here also atoms are arranged in a periodic fashion, but this arrangement, there is no definite arrangement near the grain boundary. So, definitely this surface is a distinct surface, and there will be some amount of energy associated with it. One of the easiest way of measuring or having an idea about the grain boundary energy is to heat etch. Say, suppose if you take a polished sample say, and you heat it, this grain boundary area, it will form a groove by heat etching, and if you can take a section through the grain boundary, it is possible to measure the angle. Now, this is the free surface of that grain, this is the free surface of the grain. There have been some attempt to measure that, this is known, this gamma maybe from we can get a very rough estimate of gamma is from the strength of the material, and so this is, suppose this is known. Now, what happens if you resolve this stress here? So, if you resolve, so one component which is horizontal component, this will be gamma s sin theta over 2, and this also will be of similar magnitude in opposite direction. So, this horizontal component will cancel each other, but the vertical component they will add up together. So, that is why, and there will be an equilibrium between these forces, and so that grain boundary energy will be something given by this. And it has been found that usually this free surface energy, which is rather high, this is of the order of 1.5 joule per meter square for certain for many materials. This may be of this order, and in that case this grain boundary energy, that angle, it depends on the angle, and roughly we will take it, this will be 1/3 of this. So, around 0.5 joule per meter square. Now, compared to this coherent boundary, like coherent boundary, one coherent boundary we looked at is stacking fault energy. So, across the stacking fault, that atoms, and there is some regularity, maybe that stacking sequence is disturbed, but still there is a regularity in the lattice, and so that energy, on either side there is a perfect crystal to lattice matching is there. So, this boundary is a coherent boundary. Similarly, twin boundary, the twin plane around that also they are perfectly coherent. Now, this coherent boundary will have much lower energy. As against that coherent boundary, the grain boundaries normally we consider they are incoherent, in the sense it is impossible to find any regularity in the atomic arrangement across the grain boundary. That is why we call it incoherent boundary, and incoherent boundary will always have higher energy than coherent boundary. Now, let us look at how these boundaries can form, or what are the different types of boundary. One extreme case that we looked at is a stacking fault energy. That stacking fault is one boundary which is perfectly coherent. Now, are there any other coherent boundary? Now, we did look at the stress field, nature of stress field of edge dislocations, and how these how the stress field of one dislocation interacts with another. And we have found out, if you have a dislocation over here, another dislocation somewhere here, in that case this dislocation will experience a force, and the direction and magnitude of the force will depend on the distance between the two and also their location. Like here, if it is located over here, you will find that there will be a climb force acting on this, which can help it to climb, that dislocation to climb, and there will also be a repulsive force which will try to push this dislocation further apart. But if you have a dislocation over here, in that case, true, it will have a climb force acting plus another force of attraction which will try to bring it somewhere here, and this is a place which is a position of equilibrium. So, if you disturb it from this position, move the dislocation slightly this way, there will be a restoring force which will try to bring it back. So, this is a very stable configuration. In fact, such a configuration is actually found in many crystals, and particularly in anneal crystals you do find in this kind of dislocation arrange, say which has been a piece of metal which has been deformed and given some amount of thermal activation, you do find this kind of arrangement. And this is, so pictorially you can visualize this, you have this dislocation here, another dislocation above it, another above it, and when you arrange this dislocation like this, several of these, then obviously you are going to form a tilt boundary. That is, two part of the crystal will get tilted, they will get tilted, and there will be the rotation, and the energy of this boundary is very easy to calculate. how will you calculate this boundary energy? Say suppose you can think about that dislocation, it has an unit length, and we know that each dislocation has certain amount of elastic energy. So, we can know, say suppose within this volume there is only one dislocations, and then so this particular area, what we can say with this area, this length and perpendicular to the plane of this drawing, say this is the boundary which is perpendicular to the plane of the drawing. So, it is possible to calculate the stored energy per unit area of the boundary. So, now for that first step that you need to do, what is the distance between the two dislocation. Now, this distance between the two dislocation, it is very easy to find out. Say the two dislocations, if so basically if you have one dislocation, there will be a displacement in this direction. So, if you have one dislocation, the displacement is b and b over h is the angle. So, basically, so roughly what we can say, if there are two dislocations, if there are these two two dislocations, they will be pushed apart by a slip vector b, and so therefore, obviously you can calculate this displace that angular rotation. This will be this b over h. And now, it is very easy to calculate this elastic energy of this dislocation, which is shown here. What you do is you try and find out that we have just seen that theta is equal to b over d. Now, we know that elastic energy of this dislocation is actually made up of two components. It is the core energy plus that elastic energy surrounding the dislocation. If you have a dislocation here surrounding this zone, you have that because of the elastic stress field, that energy. Now, this expression has already been derived and which is shown over here. And here if we assume that this core is of the order of the dimension of the core is of the order of the Berger vector, in that case core energy will be this is the part which is giving the core energy, this times this is the energy of the dislocation core, and this is the elastic stored energy for this dislocation. And what will be the size? The dimension will be the distance between the two dislocation, this distance between the two dislocation d over here. Now, this d, you take d by 2 here, d by 2 here. So, this is the one, and imagine the perpendicular, imagine that perpendicular to the plane is the boundary. In that case, the energy is given by this, and here you can substitute the value of d. So, d is b over theta. So, if you substitute b over theta, so you get 1 over theta, and r 0 is equal to b if you assume, then you get this expression. So, therefore, here you can, so this is the energy per unit length of the dislocation. Now, you have to multiply by this by this distance. So, if you multiply this, then you get this energy per unit area of this boundary will be equal to theta this so in that case, this will be the boundary energy. Now, one important thing is this boundary energy is equal to this low angle boundary energy. It is proportional to, therefore, that mismatch, that orientation mismatch, that 1 minus ln theta. So, this is a function of theta. As you can clearly see, if the theta is 0, then energy of the boundary, I mean it will be 0, but as theta increases, then you can say that energy, boundary energy will increase, and always we think about low angle boundary where that mismatch is of a very low, maybe maximum of the order of 5 and 10 degree around that. But if you extend, if you assume that it extends beyond that, of course, there are a lot of approximations when in this derivation. It is possible to show that this energy, it increases with theta, but there will be a particular value beyond which it will start decreasing. If this is the relationship which you can show, that in this case if you differentiate this with theta and equate this to 0, you will find at a certain position this will be maximum. Of course, this will overestimate that value quite, because there is some built in assumptions in this derivation. Nevertheless, this type of concept, that low angle boundary, that does give you an idea how to estimate the boundary of energy of a grain boundary. Now, how can you visualize? Is there a way we can visualize or classify the grain boundary according to the orientation of the grains and the surface on which they meet? There have been several attempts, and one very simple attempt is what they try to do. They visualize two crystals. Say if you visualize one crystal here, and this is another crystal which is side by side, which forms a boundary. Now, point is, if you extend, say suppose this is the boundary. Now, this is the atomic arrangement here is like this. Now, if you extend this structure even beyond the boundary, so that means this is an hypothetical construction, even beyond the boundary, you make this type of construction beyond the boundary, which is basically is a totally hypothetical construction. In the same way, you can also extend this boundary as well. This also you can extend beyond this. And this construction, it is very easy to do it even in a computer, using what you have to do. You assign on 2D, it is quite easy. You assign some coordinates here, and assign these coordinates, and one of these, keep this fixed, and suppose you rotate it, give a rotation, and this rotation matrix you have to visualize, and multiplying that when you rotate the matrix, rotate this array, it is possible when you give a rotation, it is quite easy to calculate the coordinate of these points when you give the rotation. Now, so with that, if you just superimpose, you may find there will be some points which will be lying one over the other, and this is what is shown over here, and this concept is called coincident site lattice concept. Coincident site lattice is actually non-existent. What you are saying is that you are trying to visualize what will be the energy of the atom, and for that what has been done here, this white array, there are two arrays, white one is one grain, and this red points, this is the another grain, which is not so clear, but I do not know whether this is clear. Here you can see there are arrays here. Here this is one grain and this is the other one. this is the other one. Now, some of the places you will find the 2 points they are coincident, like here. Now, if you join these coincident point, in that case you generate that coincidence lattice, which is actually something like this. So, if you have certain case where these points both are but you will find that this dimension is much larger than this lattice, where this is one grain boundary, one grain, first grain, this is the lattice point of the second grain, but this second grain there are other points also for the second grain which are oriented like this. Similarly, the other one are also oriented like this, say maybe there are other points oriented like this. And in that case, what you can find out? You can find out dimension of this coincidence lattice. So, this is the planar dimension, and in this particular example what I have taken here, there have been the 2 simple cubic lattice. So, both are simple cubic structure and they are rotated by a particular angle, and this angle is 36.87. So, when you rotate by this angle, then you generate say certain points which are coincident, and you can measure this, and in this particular case the dimension of this is shown over here, this arrow. So, here one direction you get one lattice, another direction you get 2 lattice point. So, therefore, what you can say, this lattice dimension is from here to here. So, this is the coincidence lattice. So, this dimension is much larger than this dimension. So, this is 1 unit here, 2 unit this side. So, you can therefore calculate this diagonal, and which is shown over here, it is root over a square plus 2a whole square. So, 4a square. So, basically, and then you can calculate the volume of this coincident site lattice, then perpendicular direction, that atomic distance is still a, because that is we are not disturbing, it is only a 2D construction, because boundary it is 2D. So, basically, so with this is where we can calculate the volume of the coincident site lattice and divide it by the volume of the normal lattice, which is a cube. So, you get 5. So, this we define a term called sigma. So, sigma is basically is a ratio of the volume of coincident site lattice unit cell over volume of normal unit cell. In this case, this comes out to be 5. So, usually if sigma is low, so basically if sigma is low means if sigma is 1 for low, in that case it is a low angle boundary. There is these boundaries are perfectly coherent, and it can be shown easily for twin boundary that sigma is equal to 3, and all boundaries which have lower sigma, low sigma, they have lower grain boundary energy. So, this is one way of visualizing or characterizing grain boundary, and it is interesting. I mean, this process of rotating the these 2 grains, giving a relative rotation, it is possible to generate different types of sigma boundaries, and usually the lower one are some of these which has been mentioned, but there can be many other which where the coincidence lattice sites they are much larger. So, obviously, they will have much higher energy. Now, we have talked about stacking fault quite a lot, and there is a lot of similarity between stacking fault and stacking fault and twin, and stacking fault energy is quite easily determined, and one way of estimating stacking fault energy is by measuring the distance of separation between the partial. So, we have seen that if you have a dislocation here, so basically this is a perfect dislocation, this is B 1. So, basically it breaks down into two partials B 2, B 3, and the two will have some angle. Now, this is of type, we know that this B 1 and B 2, they are of the type 1 1 2, both of them. So, only thing is and they will subtend a particular angle. Sorry, B 2 is 1 1 2, B 3 is also another 1 1 2 with a different order, say maybe 2 1 1, something like this. So, this in that case what will be the plane? So, plane you have to imagine, I mean whether these two are can lie in a particular plane or not. So, that you have to check. It has been just written without confirming, they need not be in the same plane, but in a particular plane we know that here there will be 3 1 1 1 2 directions, like these directions. This is a 1 1 2 direction, this is another 1 1 2 direction, this is another 1 1 2 direction. So, if you extend this and extend that, and this angle will be 60 degree, because these are each of these they are subtending equal angle in a plane. So, that angle is 120 degree, this angle is 120, but they are actually, if you extend this angle is 120, but you extend this angle is 60 degree. Now, the question comes up is it possible to measure this distance? Now, this will depend totally on the magnitude of the stacking fault energy. If this stacking fault energy is low, this d is large, and in that case possibly it can be seen with maybe within the resolving power of the microscope. Under TEM you can see these two partials separated by a fault, and faulted region also gives stacking fault fringes. So, this is one way of finding out the stacking fault energy, but this will be applicable only in cases where the stacking fault energy is very low. But there are materials, and we have talked about it, there are materials where the stacking fault energy is very high, and these materials they can cross slip. Here the dislocation can cross slip easily. Suppose a dislocation which is moving in a plane here. So, these are the partials. So, if it meets some obstacle over here which is not allowing the dislocation to move, these dislocations, a part of it, if you apply this, they can join together along this particular line. It can come here. So, basically it can then move, it can come here and it form a constriction, and this can say if this is the another plane which is intersecting slip plane, it can move there. And this is what is shown in cases of material where the stacking fault energy is high. In this case, the dislocations moving say in one plane is a delta, another say in alpha. So, they can meet along the line BC, and they can intersect. This is one dislocation moving here with a Berger vector say DC, and this can intersect a dislocation moving here having Berger vector B c, and they can create a constriction, and when such constrictions are formed and rest of the part, these nodes are formed and rest of the part they split, that means they split on these planes. In that case you can generate this kind of dislocation networks, where these dislocation, these are nodes and these are partial dislocations, and here these partial dislocations basically they will try, there will be some force, repulsive force that will try to push them apart, plus depending on the energy that it will try to minimize that, it will, because the fault which is created, it has a certain energy. So, that will exert another opposing force, will not allow it to grow. So, you have some situation like this, where you may have this dislocation lines which are curved, and if you can measure this radius of curvature, it is possible to calculate the stacking fault energy, and which is shown over here. This is the line tension, the stacking fault energy is equal to the line tension over R, and here the line tension energy which is given as alpha G B square. So, many cases looking at transmission electron microscopic examination, it has been possible to estimate stacking fault energy. And now, let us now take up a case where in very often we have seen that experimental measurement of dislocation, we can also measure the dislocation density. Now, dislocation density means many times we define a term dislocation density, and usually it has been mentioned these dislocations they will intersect that plane, the top plane, let us say this is a perpendicular plane where these dislocations they are intersecting, and this is the number of these intersections, that means number of dislocations per unit area. This is the dislocation density. Now, in that case it is possible, if you know dislocation density, it is possible to relate it to the magnitude of shear strain, and which is shown here. If one dislocation moves from this end to that, that means if it moves a distance x 1, it creates a slip step of magnitude b. So, therefore, so this is b over so basically, so this is b, you create a b, but all dislocation may not move the distance x 1. So, that means it does not move from one end of the crystal to the other. It is quite likely dislocation will move a fraction of this distance, and suppose that distance a dislocation moves, we consider the dislocation ith dislocation. There are several dislocation. Let us consider a specific dislocation I, and that can move a distance delta I. Then the strain that it will generate will be delta I b over x 1. So, this will be the magnitude of the step that will be created, and if you divide by this distance x 2, then you will get the shear strain. So, actually what is happening? The shear happening means, how do you find out shear strain? Shear strain is this step, this is the step. So, if it is delta I times b average distance over x 1. So, so this is actually is the size of the step. If you divide by, say this is the dislocation I dislocation. So, therefore, if you divide this by x 2, so in that case gamma I comes out to be delta I b over x 1 x 2. Now, this is one dislocation. To get the total strain, what you have to do? You have to sum over all the dislocations. So, I equal to 1 to n, and when you sum up, then you get this, and if you can say that average distance a dislocation can move is delta bar. In that case, this is, and we can say this is the number of dislocations over the area. In that case, we say that this is the density. So, this is, so in some so therefore, we can say that total shear strain is equal to rho b, the distance a dislocation moves, average distance a dislocation moves. Very often, I mean, we are using these symbols, but it may vary from book to book, but basically what we say, the strain, shear strain also will have a direct relationship to longitudinal strain, and we can approximate. So, that means that strain is proportional to, or strain is equal to rho b and then average distance a dislocation moves. And in that case, and if we say that strain rate, if we try and convert it into strain rate, in that case it will be, strain rate will be rho b then x dot. So, that is the velocity of the dislocation. This is the strain rate. Now, dislocations are always present, I mean, in the material, and they can form a network of dislocation, and you get a very stable network in cases where you have a high stacking fault energy and something like this. And in this case, it is quite easy to show that rho, we have seen this expression rho. So, you can visualize. So, these are the pin dislocation, they can act as Frank Reed source. The yield stress or shear stress at which deformation takes place will be this, and here L is the link length. And it is quite easy to show that dislocation density, this L is actually equal to 1 over root over this dislocation density. So, therefore, what we can say that tau, that yield stress is equal to G b root over rho. So, that means as the dislocation density increases, the shear strength of the material increases. Now, another important thing is to consider the movement of a dislocation in a periodic lattice, and we had made an approximate estimate in the sense that if you look at a lattice and if you try and introduce a dislocation, you will find the top part is under compression, bottom is under tension, and therefore, we said approximately to move in such cases, to move this top part you are doing a positive work and bottom you are doing a negative work. So, therefore, net work is 0. So, stress to move a dislocation in the lattice is nearly 0, but in fact, it is not so. Actually, you have to move the dislocation in a lattice where atoms are arranged periodically, which is shown over here. Therefore, you will be some additional friction force will be required to move the dislocation, and this is particularly shown over here. This dotted diagram is a perfect lattice, the no dislocation. Now, if you try an extra plane, you get these lattice lines, they get distorted, and this distortion persists over a length, and this length is called the width of the dislocation. Now, it is possible to show that this force or stress required to move this dislocation will depend on the width of the dislocation, and this has been done by actually Pearl and Nabarro. They estimated with some approximation. That means, we use this particular approximation that while to calculate strength of an ideal crystal, we have seen that tau equal to G over twice pi sin 2 pi x over b. So, if you look at that shear stress, there are certain position of equilibrium at b by 2. So, when you displace it here, displace it slightly, you know, it is still try to come back, but when it goes close to this halfway, then you can say it is a stable configuration. So, with this basically, if you have to move that dislocation through this periodic lattice, you will get or experience an additional you have to overcome an additional force, and they have found out that this tau is equal to this. It depends exponentially on W. So, you can just substitute. So, basically this Pearl stress is proportional to exponential, this is width of dislocation over Berger vector. Now, this width, if you say that this width in particularly metallic crystals, they extend over several atomic distance, maybe 10 say it will be, say dislocation code itself sometime we take is a 5b. So, it may be little more, maybe 10 times that. So, if you substitute that, you will find extremely low, say suppose even if you substitute, let us say 5b is the dislocation width. In that case, if you say 5b, so e to the power minus 10 2 pi or pi times 10. So, 30 e to the power minus 30. So, that means this stress is extremely low. We finish our discussions or the lectures on crystal defects and how these defects affect material properties, and later on we will see there are few other interactions which we have not considered, like how does the dislocation interact with point defects, because this also will be associated with how the defects can move in crystal, and maybe later stage how this dislocation at the vacancy and interstitial or solute atom can interact with dislocation. We will take up later when we consider strengthening mechanisms or methods or strength of alloys or actual materials. Thank you.